My name is Fabio Niephaus. I work on the GraalVM team at Oracle Labs, and I'm super excited to be here. It's my first time at JSpring, and I'm going to talk to you about GraalVM and WebAssembly. Right, so the things I'm going to show you, that's all brand new stuff that we've been working on. Some of this is experimental. Some of this is arguably a bit crazy, but bear with me, and I hope you enjoy the live demos. So let me start with introducing you real quick to GraalVM. GraalVM is primarily known for its native image ahead of time compilation, and that is good for more than just fast startup. So it's also great for low resource consumption, predictable performance. You no longer have a JIT that can change the performance of your application. By compiling everything ahead of time, you can reduce your attack surface. You cannot easily extend the application at runtime. And because everything is a single executable, it's more easier to deploy this in a cloud. And of course, GraalVM is supported by the major microservice frameworks and by major cloud vendors. Okay, well, hopefully you already know a little bit about GraalVM Native Image. What you maybe not know so much about is WebAssembly, short Wasm. So let me briefly introduce you to that too. On the website, it says Wasm is a binary instruction format for a stack-based virtual machine. That sounds kind of crazy, but if you think about it, it's really just something like JVM bytecode, right? Like it's some binary instruction format that will be interpreted by a virtual machine, and it's happened to use a stack. What's cool about this is also it's a portable compilation target, which means other languages can compile to it, and then you can run it independently of the underlying platform. So again, this is like JVM bytecode. You can compile Java to JVM bytecode, but you can also compile Kotlin or Scala and other languages to JVM bytecode, right? So lots of similarities here. What's really cool about WebAssembly is you can run it in the browser, even on mobile devices. And also in the last couple of months, server-side Wasm has gained traction. And the goal there is to allow you to do cost-efficient deployments in the cloud. And of course, you can sandbox WebAssembly to execute untrusted code. So I thought maybe I'll show you something more tangible to give you an impression what this looks like. This is arguably a bit crazy, but it's the tool from the WebAssembly website. There's this WebAssembly text format that you can see here, and that just defines a new method, add2. And it takes two parameters of an integer 32-bit, and then it returns an i32 result. And what it does is it gets the first parameter, gets the second parameter, and adds the two numbers together. And the last thing is the result. So on the right is the corresponding Wasm code that's been produced. And on the bottom left, you can see JavaScript code that instantiates this Wasm module, imports the add2 function, and then calls it with different values. And then you get the result of this on the bottom right. Right, so this is all you really need to know right now, or at least you have seen what WebAssembly looks like. The vast majority of users don't need this. They will look at something different, or they will look at real applications. So let me show you a real application. This is a library for photo processing, image processing called Photon. It's written in Rust, and it's then compiled to WebAssembly, and it runs in the browser. The time you see here is the time it takes to render the image in the browser, and I can apply different filters. Right, so that's kind of cool. And it's written in Rust, and then it runs on the client. Right, so I don't need a server for this. This is a static website, and it runs on my computer. Okay, so why would you want to do GraalVM? Well, we call these native executables that you can produce native images. So we thought we call this GraalVM web image, right? You can produce web images. They are using Wasm under the hood. And of course, you can run Wasm and including Java on the client, including mobile devices. So you don't need to ship necessarily a service or run a service. And for certain things. I will give you an example for this later on. Then I already mentioned cost-efficient deployments. The major cloud vendors are working on different Wasm clouds, Wasm-enabled clouds, and they are all managed. So what's cool is with a native image, you still need to put it in a container, and then you need to keep the container updated. But if you're using something like this, then the runtime will be managed, and all you do is you provide your Wasm module, and they will take care of the rest. And of course, you benefit from all the things that we already know from native image: fast startup, compact packaging, minimize attack surface, and so forth. The last thing is language interoperability that I want to mention here. That is something that Wasm is also trying to address. And here the goal is to reuse as much Java code as you can. So if you have Java code written already and you want to use it in a different scenario, but also maybe in a different language, you can compile your Java to Wasm, compile its other language to Wasm, and let them interop with each other. Right, so that's something for the future, but that's also something that we can potentially do with WebAssembly. So after showing you some demos from the WebAssembly community, I now want to show you something that we can do today with GraalVM. So in the past, we have shown hello worlds with native image. So of course, then people went on and were like, okay, it can only compile native image, can only compile hello worlds. So we figured we compile something that is much more complicated than a hello world and known to every Java developer, namely Java C. That's the Java compiler, right? So what we have done is we have compiled Java C, and we can run it in the browser. So this is Java C in the browser, and here's just a simple hello world now. And when I click compile, it is compiling this Java sources to JVM bytecode in Chrome, right? So that's kind of crazy, right? So let me show you, like let me put in a typo, and now I get something familiar to you, hopefully, right? An error, even mentioned here. But if I compile it, I can also disassemble it with Java P, and then we can look at the JVM bytecode it has produced. Here's the string that was in there, right? So let me change this a little bit up. Hello, JSpring 2025. So I'm not faking this, right? So I can disassemble it again, and then we can see JSpring. Cool. So now I can download that file. Now in my download directory. And I can go to my download directory. Here's the file. That's the hello Wasm class. So now I can run Java hello Wasm, and here's the result. Right? So this is a bit crazy, but we'll take this to the next level. Okay, if you think this is crazy, be with me. I told you that we can compile Java bytecode to native or to Wasm. This is Java bytecode, right? So we can compile that again to WebAssembly. Let me show you how that works. All you do is, this is the experimental flag that we have right now, tool Wasm. So all I do is I use exactly the same command that I used for to run it on Java. I replace this with native image, and then I add the option, because otherwise I would get a native image, but I want a web image. So now I'm kicking off a web image build. This builds our hello world, and it shouldn't take too long. It's actually pretty quick, so just 6.4 seconds. If you heard that native image is slow in building, we've gone a long way to make it really, really fast, right? So now I can run our hello world on Node. Right? So yeah, that's what we can already do. We can run the Java C compiler. We can run it in the browser, but we can also run it on Node, of course, right? So in here, I also have a little script that essentially runs Node with my Java C compile to WebAssembly, and then I pass in a hello Wasm Java file. It then compiles it and outputs the file onto disk, and then I do Java hello Wasm, and I get the result from that program, right? So I can not only run Java C in the browser, but also directly on Node. Well, I said this is a bit crazy, but in reality, it's actually a pretty damn good use case, I think. And we have a real use case for it already, which is our Graal development kit from Micronaut. We already had a CLI, a command line interface, that allows you to create new projects for Micronaut and Graal Dev Kit. And we wanted a launcher, similar like the Micronaut launcher or the Spring initializer. We wanted that. But then we need to rebuild everything in some front-end language. And instead, we decided to compile the command line interface into Wasm and then sprinkle some pretty UI in the browser around it. But if you create a project on the right, it will actually invoke the same code that's also been used in the command line interface. What's really cool is, unlike the Micronaut launcher or the Spring initializer, we don't need a service, because running a service in Oracle is kind of hard, right? I need lots of approvals. This is much easier because I can run the same code on the client and I just ship the client code, right? So in case you have no idea how GraalVM works, I quickly want to recap and explain that to you too. So we take all your application classes and libraries that you have. We take JDK classes and we have our own runtime components like a garbage collector. Then we run a points to analysis. It will trace through the entry points of your application, will run initializers as much as it can, so everything is already ready to go. Then it will create a heap snapshot, because a native image also consists of a Java heap, pre-initialized, and then it does that until it has reached a fixed point. And then at the end, the heap is written out, and the Graal compiler compiles everything that has been found reachable, to native, and that's your native executable. In the case of WebImage, we simply just changed what the Graal compiler produces. So we still get an image heap, but we don't get native machine code, we get WebAssembly instruction. Right? So it is a lot of work to get this done, but we didn't have to rebuild everything. It's still the same pipeline. So what do we want to do in the future with this? It's a preview feature of Oracle GraalVM at the moment. Well, right now, the Graal compiler targets the Wasm GC proposal. That is an instruction set in WebAssembly that allows to run or reuse the garbage collector of the runtime. We need this to make Java fast. So that's what we're already using. Right now, we only support JavaScript embeddings, so you can only run this on Node or run this in the browser. But in the future, you want to directly talk to the WebAssembly module. So that's something that we want to do. Our hello world is actually only a megabyte in size. That's smaller than the native image of the same thing. And that's even before we ran any optimizations on it. So we're currently very happy about this. So it uses the garbage collection proposals and exception handling. We can do interop with Java and JavaScript. It can include any JDK code at the moment, but we are substituting that code accordingly to make it work in the browser or Node. What doesn't work at the moment is threading, networking, graphics, and other things. So that's something that we still need to figure out. WebAssembly has the WASI proposal, which adds system call-like things, and we will be able to use that to implement networking and threading, etc. And then in the future, we can run something like Spring Boot on Wasm. Yeah. No, the Photon project is completely independent from GraalVM. That is something that someone has built in the WebAssembly community, and I thought it's interesting to show that, just as an intro for WebAssembly. It has nothing to do with Graal. Oh, of course. You could do the same thing, yes. You could render like AWT components in the browser and and get that to work. We just need the resources to work on it, right? So the good thing is all of this is already open source and maintained as part of a GraalVM Community Edition. So if you want to contribute, feel free to reach out. But of course, contributing is not always an easy starting point. A better starting point is probably you trying it out. So you can try it out today. Just download a GraalVM 25 EA build. For example, using SDKman. You also need this thing called Binarian, which you can, for example, install with Homebrew. And then you can use this tool :svm-wasm option. That's the experimental option to build Wasm modules. Okay, so this is GraalVM web image. And now I also want to talk about, in the second part, about something related, but also very different. Right? So we also have a Wasm runtime written in Java, which we call GraalWasm. And that one allows you to stick Wasm modules into your Java application. Right? So we produce Java to Wasm. Now we put Wasm into Java. Right? So that's important to keep in mind. Let me show you a demo. Oh, I already started the service. So here is a little Spring Boot application. We're going to take a look at the code in just a bit, but it's using Photon. So it's using that image processing library that I've just shown you. So I can do Obsidian, which is one of their filters, and I can apply the Obsidian filter to the image. I just use these daisies as an example image, right? And I can apply different effects like flip H, which flips it horizontally, or flip V, which flips it vertically, right? And this is the Photon that I showed you earlier, but embedded in Rust, embedded in a Spring Boot application. So this is Rust code compiled to WebAssembly and then put into a Spring Boot application. How does that work, right? So let me show you. We have a demo application and, of course, a demo controller. So this is our demo controller. It only really has a single endpoint, photo, and then an effect name. And then it implements, or it uses a Photon service. This Photon service has a process image method with an effect name. No, my IDE is letting me down. Oh. Okay, let's try Photon service. So this is the Photon service and the process image function. So what's happening here is we take some magic photon object of a pool, and then we interact with that object. We ask it, do you implement the effect? If not, then you give an error and not found. Otherwise, we create an image, these daisies, and we apply the effect to it, turn everything into a byte array in Java, and that will be our result, but we also need to free the image because this is not garbage collected. And then we put the Photon instance back into the pool. Why do we do pooling? Well, we want high throughput. So Spring Boot and Micronaut, for example, they are using they're serving requests in multiple threads, and you want every thread to have their own Photon instance, right? So what we can do here to increase throughput is create a pool of n Photon instances, so every thread can have their own when they are serving a request. So that is something that our languages can do, including GraalWasm, meaning I can create multiple instances of the same application in the same process. We cannot just do this for WebAssembly, we can also do this for JS and even for things like Python. Right? But so far everything looks like Java code. Well, because it is Java code, and we can look at the Photon class, and the Photon class is actually a Java record. And it has access to the module, the Photon module, and it also has access to the image content, like these daisies. Right? So that's what's stored inside of this object. So it knows how to create a daisies thing. But everything else is just interfaces because we're actually using the JavaScript binding. So when we compile when we compile Photon, and I've done this here with my build Photon, or I ran this wasm pack command, and then it creates files in these are the photon sources. It creates files in here in the, I think, the create package. Yes, it creates a photon.js file. This file marries the binding, which is called photon binding.js, marries it with the photon wasm backend, the wasm code. That's what's going on here. And photon binding has then again lots of utilities like flipv and fliph, and they are calling into Wasm. So that's what the Wasm community does with language operability at the moment. Like everything is geared towards the browser and JavaScript, but in the future they will change this. However, not a problem for us. We have a JavaScript runtime too, so we can run the JavaScript binding on the JavaScript runtime and the Wasm code on the Wasm runtime and include all of this in here. Right? So yes, it's a bit crazy, but if you think about this, this is relatively straightforward to do. And if you want to do it in a different approach, you would have to compile the photon library into a shared library for every platform that you deploy on, right? And then you need to use something like JNI or Panama to interface with it. And we all know this is also kind of hard to do, right? And then you need to ship architecture-specific jars and whatnot. Here, we can just ship this one photon Wasm module and the JavaScript binding, and it will work on all platforms. And actually, what I'm running here is not running on Hotspot or OpenJDK. It's running as part of a native image. So all of our languages are compatible with native image, and this is a native image with everything compiled in. Okay, so that was a lot, but we are not done yet. Haven't we done something super crazy here? And isn't that like really complicated if there is a problem, right? Like how am I going to debug this? Right? What if the pixel is incorrect? Right? Well, our languages support debugging, not just one protocol, but multiple protocols. So let me close everything and let me run on with the inspect protocol on native. Okay, service is up. Fantastic, instant startup. But this time we actually have a debugger session. IntelliJ has an integration for the Chrome inspector, which I'm going to use, but I can also copy this into Chrome and debug in Chrome. I don't like Chrome that much, but I like IntelliJ. So I click on this, and what I see is some weird uint8 erasing. Well, that is explainable too, because in our pool where we create our photon objects, it's the first thing that we evaluate. We just want a handle on this class, so that's the first thing that we evaluate, and after that we evaluate the photon source. Right, so the debugger holds at the first execution, and here we are there, and now we can take a look at the scripts loaded. So when I now resume, the application now comes up, and it's loading all those additional files. What I haven't told you is that the photon that I'm using here, I actually built this in dev mode. So this includes debug information. And our runtime can use the debug information and show it in here. So in our IntelliJ idea, we can see every Rust dependency of this photon module. We can also find the entry point. And I have gotten a bit lost. Not here, not there, right here. Okay, so this is the JavaScript file that we've seen before, and this is the binding JavaScript file that we've seen before. So now I can go to fliph, and I can put a breakpoint here, and I go back into the browser, and I'm gonna hit the fliph effect. No, that didn't work. Okay. Put it in fliph. Okay. Let me try this again. Right, I had breakpoints set already, and then it's a bit confused. oh well, that part is not going so well, but I have a fallback. Let's just do the same with VS Code. Oh, it's because there's already something running. I see. Oh no, it's this one. Okay, let's do this with VS Code and debug adapter protocol. I can actually do the same and connect with debug adapter protocol. You will notice, oh, this looks familiar. And I can resume, and then lots of scripts are loaded. Same thing. So let me see if I can find it. Here's the binding file. Yeah, it doesn't know that this is JavaScript. So now we search for flip H. Put a breakpoint. Okay, here we go. So now we are debugging the JavaScript code that's embedded in the Spring application. All of this compiled to native. We are in the JavaScript binding, right? And now the crazy thing is, I can step into this. So I step from JavaScript into Rust, right? And I'm actually stepping into a Wasm bindgen generated frame. So this is something that the toolchain has created for us. And then we see a lot of craziness from the Rust compiler because there's methods that are force inlined. So we need to step over them. But then we end up in the Rust code that implements flip H. And here we can see what it does. It gets a photon image, which is this thing. That's a Rust object. And it has a width and a height. So it gets the width and the height, creates a new image, and then it iterates through every single pixel and puts the pixels to the other side. That's exactly how you would try to implement this, right? So what's cool though is this is a full debugger, so I can change stuff. So here's the pixel. This is the first pixel. It's the first pixel on the top left, which is going to be on the top right. It's an RGBA value. I can change this to, let's say, red or maximum red. Maximum red. 128 is too much. Let's just 127. Then 0. And 0. So no green, no blue, but we want full alpha. Okay. So next pixel. Let's go to the next pixel. Let's do one more, or maybe two more. So we do this to that. And again, one more time. We're now at pixel number 0, and Y is 2. Ooh. So I'm just putting more in here because otherwise it will be a bit hard to see. And then I just resume and go back to the browser, which is loading the image. And great success. Okay, so we can embed WebAssembly in Java applications. We cannot just do this with Rust. We can also do it with Go, with C++, C. We have all of these demos up on GitHub. You can try them out yourself and understand how we built them. It's not that hard, actually. Yeah, they work in Spring Boot, they work in Micronaut, they work in Quarkus. So let me quickly introduce you to GraalWasm itself. So that's a WebAssembly runtime written in Java. It's actually built on our Truffle framework, which we've used and built for a couple of years ago, and it's still like being actively developed and still making our languages great. Like the debugger is implemented on the Truffle infrastructure, and we got this for free when we implemented WebAssembly. WebAssembly has a spec. We implement the first version. That's also the only spec that's really public. And we also implement a bunch of feature extensions. We don't implement WasmGC yet, but many others. You can use it to do portable native extensions, right? You can compile your native code, your C, C++, Go, Rust, whatever native code, compile it to Wasm, and then you can ship that one Wasm module to all of your different operating systems, right? You don't need to do platform-specific native extensions. We have a JavaScript integration, so you can use these JavaScript bindings easily to facilitate high-level language interoperability. So Java can talk to Rust on Wasm through JavaScript and exchange complex data structures. That's what we have done with this photon object, right? That's a complex data structure. It's the fastest Wasm on the JVM thanks to our Graal compiler. So our Graal compiler actually acts as a JIT for WebAssembly, and it will speed up your WebAssembly code. So even though this is was all compiled with debug information and in debug mode with not many optimizations on, the Graal compiler can start optimizing it and make it really, really fast, right? And that even works in a native image. So the native image that I've just used actually has the Graal compiler compiled in, and then it starts JITting WebAssembly. It's not JITting Java, it's JITting WebAssembly and JavaScript. And yes, of course, all of this is 100% Java. Right? So we don't have any native dependencies, any external dependencies. It's just a bunch of jars. It's actually jars on Maven Central. So all you need to do is add these dependencies to your Maven or Gradle build configurations, right? And here, for example, I declare a dependency on Polyglot, which is the our API to interact with the languages. And then I say I want to load Wasm, but I can also say I want to load Python and JavaScript. I can also load more than one language if I want to. GraalWasm has actually been around for quite some time. We launched it in 2019 as a research project. Last year, it has reached a stable status, and it's now ready for production. So it's supporting many standardized features. It's actually listed on the WebAssembly website, right? And you can check what features are supported. That sometimes is necessary to know so that you know what you can use, what you should like compile your Rust code to, for example. It's all embeddable in Java. It can even be used as a standalone runtime if you just want to run Wasm. It can do this JavaScript language interoperability thing. We are working on the SIMD proposal, which will essentially bring what we are going to get in the Java space with Vector API to WebAssembly. So you can use SIMD instructions to do really fast, for example, image processing. That's very interesting in Wasm for a lot of cool applications. And we have support for draft debugging, which I just showed you, right? So it works in VS Code. It typically also works in IntelliJ. I was at JetBrains on Tuesday and at the conference, and I presented this in IntelliJ, and it worked just fine. I have no idea why it didn't work today. It's not their fault. It's probably just me. Okay, so to conclude, GraalVM Web Image. You can use GraalVM to generate Wasm GC modules. So WebAssembly modules using Wasm GC. You can build these modules today with a GraalVM for JDK 25 EA build. And WebImage provides Java to JavaScript interoperability, and we're going to extend that in the future. So you can also do pure WebAssembly interoperability, but JavaScript is already interesting because you can do cool things in the browser and cool things on Node and other Wasm runtimes. And then we also have GraalWasm, the GraalWasm runtime, which makes it easy and possible to extend your Java applications with WebAssembly modules, like Spring Boot or Micronaut or some other applications. And you can use GraalJS to do high-level language interactions in using these JavaScript bindings that you have seen. And yeah, if you want, you can scan one of these or both QR codes. The one on the left will take you to the Java C demo in the browser. And on the top right is actually a little ribbon that takes you to the sources. So if you want to see how we have built that demo, you can find all of it on GitHub. And the same is true for the Photon example that I've shown you. We have this in Spring Boot and in Micronaut in the demos repository. And in fact, we have a ton more demos and guides that you can read up on. If you find this interesting and you want to dig into Python, I encourage you to look at the Python directory in there, the GraalPy directory in there. We have a ton of cool things that show how to use Python AI packages in your Java application, and it works the same way. And now with that, I'm happy to take any question. Yes. Good question. I don't know. Let's find out. Okay, so let me see. So this is Java seed. It's called JS-Wasm. I don't know why. It's 33 megabytes. Yes, so that's in the browser, right? So yeah, maybe don't do this on the if you're not on Wi-Fi on your mobile phone, because it will burn your data traffic, right? But we can still get this down, right? This is not optimized, and there are tools like WasmOpt, and we can apply compression to make that even smaller, right? So your question is actually something that I did not anticipate, but it seems like you were asking about like the Java playground, right? Okay. Right. So we happen, yeah, of course. So we happen to have Java implemented in Java, which we call Espresso. So that's another one of our languages that I didn't mention because it's very confusing, right? But it's a Java implemented in Truffle, and it can compile to native. Right now, well, it's implementing a JDK and has lots of native dependencies. You would need to compile them to WebAssembly too, which is complicated, but there are tricks to get around this. So potentially, we could compile Espresso to Wasm and run it in the browser. Because you ask, let me show you my crazy fallback slide. So, well, the question is like, can we compile GraalWasm to Wasm, right? And really, like, just because you can doesn't mean you should, right? So I've drawn a circle, and of course we can go full circle. Right now, we can not compile Java to Wasm and then embed that in a Java application, because GraalWasm does not support this Wasm GC proposal yet. We're working on this. In the future, you will be able to do it, right? But what we can do, because GraalWasm is implemented in Java, we can compile that to Wasm, right? So let me find a terminal, and let me go to the Easter egg project. So that's the Easter egg project. The Easter egg project has a GraalWasm.js, that's the binding, and the GraalWasm.js Wasm module. That's the Wasm. That's our Wasm runtime, 20 megs. Not optimized, so maybe it can even be just 15, 10 megs, something like that. Then we have an add 21 and 21. We can actually look at it. That's the WAT file. I've shown you this in the beginning. It's the add2 method, and then I have a main method that pushes a constant 21 and another constant 21, adds the two numbers with that function. So that should give us a 42. Right? So now I can run GraalWasm on Node, and I can pass in, and I get 42. Right? So this is our language runtime compiled to Wasm running on Node. It's a bit crazy, but we can do it. And again, because you can doesn't mean you should. But it would be interesting with Python, with JS, or with Python, because you would be able to run Python in the browser. And if we compile Espresso, you could run Java in the browser. With other projects, yes. Yes, that's correct. Any other question? Yes? Right. Yes, so what you would need to do is you would need to use the Java debugger to debug the Java code. You can actually spawn a Java debugging session and use the guest language debugger, right? And then the moment you enter a guest language, you have to switch the debuggers. We had a prototype in the past where we combined the two, where you could step from Java and then into JavaScript and then into Rust. Right? But it's really complicated to do this because Java IDEs, they typically use JDWP, which is built for Java, but not so much for other languages. Right? So we could potentially do this in the future with debug adapter protocol, but unfortunately, debug adapter protocol is not a first-class citizen in every Java IDE at the moment. Hopefully that will change in the future, but that is indeed possible. Yeah. Right. So it's for Java projects that want to deploy to the browser and run, for example, on mobile. That's something that you can do. You can compile, like we did with our command line interface, you can compile it into Wasm and then run it in the browser and sprinkle a UI on it, and you can reuse your code. That's the front-end story. The back-end story is, as I mentioned earlier, WebAssembly is built for efficient cloud deployments. That's a goal for WebAssembly. Native Image has the same goal, right? We want you to deploy your Java in the most cost-effective way. But instead of having to compile the native and then sprinkle a container around it, you can just use WebAssembly instead and get a managed runtime. Okay. So cheap deployments is the other thing that we're targeting.
Examples of this deployment now?
Well, this is a preview feature. If you use this in production, you would be crazy. Right? So we're working on this right now. Hopefully next year we can run even more. Right? Right now you cannot even do threads. Right? So we will need to do more work, and hopefully we can get the community to contribute as well. And then maybe we can run more and more of the JDK, and you'll be able to compile more applications to Wasm, including maybe UI applications. Right? Run them in the browser. Yes, that's what they're doing today. Yes. Yeah, exactly. Okay, any other questions? Well, Scala compiles the JVM bytecode. Our toolchain consumes JVM bytecode, right? I haven't tried it, but I'm sure someone in the Scala community will. I've seen the Clojure guys going all crazy on this already. So I'm sure it will be possible to compile Scala that way too. Yes. I don't see why it can't work. Any other questions? If not, then thank you. Have a great time at JSpring, and maybe I'll see you the next time.